Hi everyone, I'm Giuseppe. I'm here on behalf actually of a whole SRE team at the Wikimedia Foundation to talk to you about one of our success stories as an SRE team, how we've progressively made a complex operation involving every layer of our infrastructure in a simple, painless, and automated process. Specifically, I'll briefly introduce who I am talking about, explain why adding a second data center and serving traffic from there was a big deal for us, and then I'll explain how we improved this process, what tools we built to improve it, and how we finally got to flow traffic through all of our data centers at the same time. Also, and I think this is the most interesting part of the talk, I'll explain how we made switching the primary data center routine operation and what lessons in SRE practice we can extract from it. Let's start by introducing ourselves. We're the nonprofit that supports Wikipedia, which you might know as the largest and more accurate multilingual training corpus for your AIs, which also dubs as an online collaborative encyclopedia that other people, the normal people, use. And we also run many other sister projects, but what I want to underline is we run one of the top websites in the world, traffic-wise, on an infrastructure that we manage from the ground up. Our footprint is relatively insignificant, if you want, because we manage traffic up to 400K RPS at peak, with a little more than 1,800 servers, on a truly shoestring budget, as you can see. These servers are distributed across 5 data centers, soon 6, and these data centers are 2 different types. The data centers spread across the globe just run our CDN caching layer, so that we can serve cached content to you from a location nearest to you, while 2 data centers are hosting our main application, and they are on the mainland US. As you can see from these photos showing the amazing work of our data center operations team, we run on physical hardware. We don't run anything on a public cloud, mostly for cost and user privacy reasons. So this means that we have to solve a lot of problems that everybody here that runs on a cloud gets for free from your cloud provider. And that gets me to the story of our first switchover, which is not a success story, if you want. Given our budget has never been particularly rich, Wikipedia was run out of a main single data center for almost 15 years. When in 2015, we decided, okay, well, our budget has grown enough, the donation has grown enough that we can actually build a second data center main data center for disaster recovery. So we set ourselves to the task of building the second data center. Now, the physical part of building the data center had basically no unknowns. We knew what we want. We basically wanted to replicate the infrastructure on the first data center. The code, on the other hand, had 14 years of implicit or explicit assumptions that everything was running from one data center at a time, and all the traffic was flowing through that. So there was a lot of stuff that we had to fix there. 14 years of tech debt, basically. And the worst part was that we were using data stores like Redis that really don't work well with replicating over a non-negligible latency, and also doesn't provide any form of encryption for its replication. And we were replicating user-sensible data, and we wanted to encrypt it over the wire between data centers, which meant that the whole thing was built with lots of duct tape and IPsec tunnels. It wasn't necessarily pretty, but everything actually worked well only if we ran all the traffic through one data center at a time. And that takes us to our first switchover. To ensure the new data center was built, we built for disaster recovery, was actually useful, and we weren't just wasting money having machines laying there. We needed to prove that we could serve a whole website from there. Doing the switchover wasn't simple. As I mentioned, all these years of tech debt that we had to overcome. And so the preparation was pretty long. So at the start of 2016, we actually did the switchover, and again, it wasn't pretty. We had to do the switchover, we had to make 15 code commits across 5 repositories. That entailed 45 minutes of read-only mode, which means for 45 minutes you were able to read Wikipedia, but you weren't able to edit it at all. Over that, we had a large number of engineers involved in the process. We had 10 people between SREs and SWEs following the process. And in addition, sadly, in addition to the 45 minutes of read-only time, we had 2 hours in which our latencies weren't ideal. We at the start even peaks of high latencies and occasional timeouts shown to the users. This was due to the fact that even with all the warm-up scripts that you want to run, when you get the full traffic of Wikipedia on a data center that's completely cold in cache, that's going to cost you. So switching back actually to our usual data center was faster because, well, we solved some bugs that we found out during making the first switchover. So when we switched back to our main data center, the procedure as it was optimized until it still took us about 30 minutes of read-only mode and a long time of performance degradation, as I said. Now, why is that? Which lessons did we extract from this process? First of all, we need to do it again, ideally every 6 months, or we won't be able to be sure that our data center is actually serviceable in case of a disaster, right? We want to be sure that we didn't have hardware rot or worse, configuration rot, that we implemented something and it actually only works because we only tested it in the data center that is actually running traffic, right? And also we would actually be wasting money if we were just keeping that data center very idle. And we are a non-profit organization living off of user donations, so we have to be careful with how we spend money. So if we want to perform these actions multiple times per year, well, the process needs to be simpler, faster to execute, and more importantly, less impacting to the user. The process was terribly clumsy, fundamentally for one reason, which is we needed to make a full complex sequence of commits to our infrastructure as a code repositories and to our actual software, and then deploy them. So run through CI, you commit the commit, you run through CI, you have to apply it everywhere, wait for the configuration management to apply it everywhere, or for the deployment software to apply it everywhere. We realized at that point that whenever you have to manage the state of your distributed system, the transitions between these states, GitOps isn't really a good pattern to follow. States need to be managed consistently, and every part of a distributed system needs to react quickly to changes in that state. So how can we improve this process? As I said, we need a central store that can represent consistently the desired state of the system and also notify every component. We set out to create such system based on 3 core tenets. One was flexibility. So our systems are in general very stable and behave correctly. Like we get maybe 1 page per week typically in a good week. So we did want to change as little as possible in how our system operated. And that took us to take the approach of using a state store, a basic building block like etcd as a state store, instead of a more batteries included approach like console that would have forced us to change more stuff in our systems. We wanted to, given we are using a basic building block though, we really didn't want to have to write directly through the etcd API our objects in the state store, right? So we wanted to create a CLI tool and potentially a Python library that people could use to safely write to this system. And finally, on the client side, we wanted our production not to be strongly coupled to this data store. We wanted our production to chug along just fine in case etcd becomes completely unavailable. I want to point out that all these choices that I'm talking about, including using a state store, aren't done in a void. There was ample previous literature on this. Just think of Chubby, right? The Chubby design as the way Chubby is used at Google has a big influence in our design decisions. So going a bit more in detail about the tool that we created, it's a CLI tool that can also be used as a Python library if you're writing automation that interacts with the data store. It's not a particularly complex tool. It actually just stores JSON documents in the backend, following a schema, a JSON schema, and as basic logical protection for input errors, or when you want to mass modify objects. We found out pretty soon that this was okay for basic operations, but if we wanted to build more complex domain-specific state management, we wanted to actually extend the tool to create specific tools, specific other tools that had a slightly different UX, more friendly for specific use cases. A couple of examples are dbcuttle, which is our tool to manage our database pools, the state of our database pools, and requestcuttle, which is a tool that we built to enable dynamic filtering of HTTP requests. But well, this tool is used to write to the data store. How do we ensure that application at all layers listen to what happens in etcd actually? So there's two approaches that we had to take. For applications that we write ourselves, we mostly try to integrate watching the data store in the application itself. But for other parts of the stack that we don't directly control, we decided to use confd to watch the etcd data store and modify files, verify the files that we created, and notify the applications. Generally here, the main thing to be careful about on the client side is also to protect from bad data. I can't underline enough how bad data in your state store can be disastrous for your system. So every application also needs only to apply changes when they're valid, and it also needs to have a local cache of a state, so that in case the state store is unavailable, it can just chug along in a state freeze state. Overall, we had to integrate the state management at all layers of our infrastructure. We'll see a couple of examples in a few, but the net effect over several interactions of these integrations was to allow us to reduce the number of code commits that we need for doing a full Datacenter switchover from 15 to 0. I decided to pick a couple of examples to show you the pitfalls that you can fall in with implementing a state store, one native and one via confd using confd. Let's start with our main application, MediaWiki, that you probably run your own wiki at home on, but it can also run Wikipedia. This application gets most of our requests. We implemented a class called SREconfig in MediaWiki core, so it's available to you as well if you want to use it, that can fetch configuration from MediaWiki. We didn't have very tight requirements in terms of consistency across all of MediaWiki, so between servers, so we decided that just doing a polling from a thread every 15 seconds, the state on etcd, and then storing it into the PHP's global memory store, which is called APCU, was enough. What we do in case of failure, if etcd servers are unreachable, they're unavailable, or they send you back corrupt data, we just refuse to update the global memory store of the application server, and we just chug along with the state that we had before. So as long as we don't need to change state or deploy the code again, because that would restart PHP, we're OK. So we can run in that free state while the data store is unavailable. The main takeaway that I want to give you is that direct integration of querying your data store, state store into your applications is the best way to go if you can, because you have more control, you have more observability, you have more flexibility in determining the behavior that you're going to use. But sometimes, though, especially for applications you didn't write or control, you have no other options than taking out the tape and start building. So one example we have is for our discovery system. Now that we have more than one data center, we want applications to be able to tell where they should reach another service. Do I need to reach it in this data center or another data center, right? Now, the simplest and most obvious globally available API for this is DNS. Now, I know we've heard, I think it's a meme of a conference that DNS is bad, and it's always the problem. And also, I think I raised some eyebrows because I've heard innumerable times, DNS is not good enough for a discovery system. And I want to say now, I agree. But we'll get back to that in a minute. We store the state of each discovery record. I just want to show you how a record looks like. So In this case here, we just have some tags connected to the object that tell us, okay, the service foobar in Datacenter US East 1, that's not the name of one of our data centers, but I wanted people that work on the cloud to feel at home, is enabled, so it can receive traffic. Any new client can cache this information for up to 300 seconds. Yes, I know this looks a lot like DNS, right? But actually, our initial idea, given I heard so many times that discovery systems shouldn't use DNS, or not only DNS, our initial idea was to actually wire this state into the control plane of our service mesh. But in the end, we never truly needed it up to now, and to this day, we're still relying on DNS. So why do people recommend not using DNS for service discovery, and why do I agree, generally speaking? Well, there's other good reasons, but mostly I think the reason is that it's quite easy to get the system subtly wrong, either server-side or, more importantly, client-side. Let's see some details of how our systems works and which pitfalls we try to avoid. So very quickly, we use GDNSD as a DNS server. GDNSD has the concept of failover pools and geolocalized pools, where you can indicate a series of IP, and if it's a failover pool, it will just get the first one that's enabled, that's up, and it will only resolve to that IP for every other service. Or for GDNS pools instead send you to the nearest IP that's available, to the client. Now, this translates pretty well to active-passive services that need to run in a single data center all the time, and active-active services that can run from multiple data centers. So how it works inside of GDNSD is just that GDNSD can watch the state of these pools by using iNotify on files. So we just run confd, confd looks at etcd, confd modifies the template, verifies that the template is still a valid GDNSD configuration, then it substitutes the state file, GDNSD notices that, and it applies it. There's another detail that we implemented, which is sometimes you could have a service that is actually unavailable, and we wanted to be able to just tell our discovery service, there's no version of this service available anywhere, and now you can tell other applications as fast as you can that, well, if all the systems are disabled, we just provide one IP for a VM that basically runs a firewall that just sends back RSTs to any TCP request that you make, so that it's very fast to tell other applications, this application is unreachable, right? It's the fastest way you can tell another service that that application is unreachable. On the client side, though, you need to make sure of a couple of things, which are that your application doesn't have the nasty habit of just resolving once DNS record and then forget about having to re-resolve it after the TTL. And on the other hand, you also want your application to actually perform caching correctly, so caching the result and not re-resolving it over DNS every time it needs to resolve a name, right? Because else you introduce a huge amount of latency in your system and for every request, and also you're probably trashing your DNS servers. Sadly, we found out that most applications out there either one or the other of these, fall into either one or the other of these pitfalls, or sometimes, amazingly, both of them. Thankfully, we had implemented the service mesh based on Envoy. We're not using Istio, but it's pretty similar. And thankfully, Envoy does this correctly, handles DNS calls correctly. So for us, in this specific situation, DNS was good enough. So building a store for state wasn't really enough, because the procedure to do the switchover is long and complicated. We do a lot of procedures there. I don't want to go through all the logical steps that are involved, but I just listed them on the screen, and each of these steps is actually quite complex and can span several hundreds of servers to act upon. Of course, we never did all this stuff by hand, but this gets me to one of the best ghost stories that elder SREs tell newer members of a team when gathering around the campfire, or actually the way they justify their worst crimes against technology, which is, this used to be a small bash script. Sadly, in this case, the script was never small. It was never readable to the uninitiated, and eventually it was hard to read even for the initiated, the people that wrote it. We knew that we needed to build a better tool to handle all this. And while we did start building for the switchover, we tried to make a tool that could we could actually use for all of our automation. We first created an engine written in Python to help SREs write their own automation called SpiceTrack. And no, this isn't the logo. It's just an image that an AI generated for me when I put SpiceTrack as an input. Now, the name, you're probably wondering why the heck did they call an automation tool, an automation framework, SpiceTrack? Well, the name, in fact, derives from the fact that under the hood, we use Cumin, which is a distributed execution tool that we created. And so the analogy would keep going. So what does SpiceTrack do? It allows us to code and run complex cookbooks, which are automated complex recipes that operate on servers, data stores, remote APIs, and so on. SpiceTrack has a lot of additional features, like the ability to query an asset and service catalogs. It has a built-in dry run functionality to test that what your cookbook would do without doing actual disruptive operations, and allows you to write rollback procedure in case your automation procedure isn't successful. So writing a cookbook in SpiceTrack is quite simple, and I want to show you a quick example very quickly. So I chose DNS again. Wow, this conference is really preparing you for my talk. So this is just a cookbook. We're writing a cookbook to wipe the cache of our DNS resolvers. And very simply, we implement two classes. This one, based on cookbook base. Sorry, this is a tongue twister for me. It has two methods. One, just adding the command line arguments, and one just telling, OK, the render class that you're going to use is this one. And the render class is as simple. Basically, the interesting things are this line here. We're querying our asset manager catalog for finding the PDNS resolvers, the PDNS servers that we have. And in the run method, we just run on this host that we just selected. We just run synchronously this command. And then we check. We have one of the facilities provided by SpiceTrack is to check a record on a specific resolver. So we're checking that this record actually resolves to the IP we want to find now on all the resolvers. If any of these fails, this raises an exception, but we have the retry decorator here that just tells us, OK, try this command 5 times at regular intervals, and if it fails 5 times, then report the error to the user. OK, back to the switchover. How do we run the switchover now with SpiceTrack in the mix? It's just as simple as launching this command, but then that brings up an interface that has 9 stages and 16 sub-cookbooks, so a very complex operation, right? We keep track of the execution time of every stage, and 1 week before the switchover, we ensure nothing has been overlooked over the last 6 months by running a live test, like how the live test works. We launch a switchover script as we are switching to the data center that's actually running traffic now. Given every operation is ensured to be idempotent, we're basically running all the commands, but they just have no effect. Or at least we hope they have no effect. Given every step in the cookbook is time, we can actually ensure and monitor that operations don't rot and don't take longer over time. Overall, now, between this and the state store introduction, the time for a read-only state is now on average under 2 minutes for our switchover. But what about the period of degraded performance that I was talking about before? Well, this takes us to our end game, which was always, and it should be for anybody running in more than one data center, which is running from all of them, running traffic through all of them. And sorry, there will be no Avengers reference in this talk because I want to actually upload the slides to Commons. Back to us. Whenever you have multiple data centers or availability zones, sorry for the cloud people, you should strive to always serve traffic from all of them. If applications can really accept writes from multiple distributed places, just do either split reads and writes, which is what I'm going to talk about from now on, because that's what we did, or shard your application somehow. So what are the benefits of flowing traffic through all of the data centers all the time? Well, first of all, you get no more cold caches, right? And this means that no more period of degraded performance, but also you reduce the risk of hardware imbalance in your hardware data center and configuration rot basically to 0. And I think this is because, most importantly, I think, it forces both SREs and SWEs in a mentality of multi-data center operations. Like, given your traffic is always flowing through multiple places that have a non-negligible latency between them, you have to keep that in mind when coding your application and when preparing your infrastructure at all times. Finally, this more or less doubles your peak capacity. Now, there's an asterisk here, because the peak capacity I'm talking about is for exceptional events. Because for your daily capacity, you should really be able to run it through one data center, because we did build the second data center for disaster recovery, right? So we want to be able to serve all of our traffic from each of our data centers. If we didn't want to do that, we would just add hardware to the first one, and we wouldn't have to do all this stuff, right? So how do we split reads and writes? In our case, it's pretty simple on the surface. We just look at the HTTP method of a request at the edge. If a method is an idempotent method, we tell the edge is programmed to send the request to an active service, so a GeoDNS located record, DNS record, that sends the request to the nearest data center to the edge cache that you're reaching. If you make a post or any other non-idempotent HTTP method request, that will be sent to an active passive record, and so always flowing to the primary. So this seems very simple, right? Yeah, not so much. One of the core tenets of a wiki experience is that you see your edits immediately, and we go to incredible lengths to ensure that when you make an edit to Wikipedia, you will see it immediately. Maybe everybody else in the world will see it in a couple of minutes, in a minute or so, but you will see it immediately. So you can understand that when you have another, I'm coming from the other data center typically, right? The latency of replication for reads is higher than in the first data center. So we risk having to send the request all to the master database, and we really don't want to do that. So the solution we found was actually pretty simple. We just sidetrack the problem. When you make an edit, Wikipedia sends back to you a short-lived cookie that tells our edge caches when you make the next request. Just send these users for primary. Don't bother sending them near to you. So one thing that I think came around during my presentation is that the complexity is given to you by your data stores mostly. So let's dig a bit into what data stores do for you. So I had a picture of a database, but actually I thought this one was more appropriate given what we're talking about. So we did have to split reads and writes because SQL databases in general aren't really great at accepting writes from multiple servers, even less if they have a non-negligible ping latency. This means that whenever you need a relational database, which is always, I think, splitting reads and writes is something you have to do at the application traffic layers anyways. While this seems obvious, there are problems with any other kinds of data stores. For example, your caches, right? Your caches in memcached needs to be consistent across data centers. Now, thankfully, Meta had these problems way before we had it. And also, thankfully, they released as open source their memcached proxy, which calls MacRouter, which solves this problem amazingly. But even when you have a distributed data store that's been designed for this, like Cassandra, right? Cassandra can work with writes, multi-writes from many places, even geo-distributed. Even in that case, you have to be very careful to match the consistency of writes that you do on the data store with what you assume in the application. If you have even a slight mismatch, you will run into race conditions. So finally, basically what I'm saying is as long as you can keep your data stores local only, that's better. Let's move on to have a quick look at how we keep the process efficient. We're now switching primaries actually every 6 months at fixed dates, so that are universal enough that every community that we have global community, know about them, which is equinoxes. So we jokingly say that, like migratory birds, Wikipedia edits migrate north in the spring and then migrate south in the autumn, because our two main data centers are in Texas and Virginia. We also want to keep ensuring that we can serve all of our users from a single location, right? So for a week after the switchover, we serve all the traffic from the primary data center exclusively. This also has the advantage of allowing us to perform disruptive performance on that data center that is now not user-facing. And we get to the thornier problem, I think, which is social, so it's thornier. When you automate things completely, there's the risk that the ancestral knowledge about how things work under the hood of your amazing automation remains with a progressively smaller circle of engineers. And no one else dares touch the code, right? Slowly, it gets to a point where most of the team doesn't really have the confidence of running this tool in an emergency, because this tool can have catastrophic consequences, right, in case of failure, and they don't feel like they own the tool. To contrast this risk, and also to keep ourselves in check, we established as a rule that the newest member of the team will run a switchover themselves when they join. The only way this can work without stressing out the newer hires and getting them to quit is if the procedure is clear, the tool gives you good feedback on what's happening, and documentation is comprehensive. Now, we just performed a switchover, and a new hire went through the procedure, right? We just passed an equinox. So I asked them for a quote for this presentation, and this is what I got. Yeah, I love my team. OK, time to wrap this up. Let's see what lessons we can learn from what we've done. So the Latin poet Lucretius said, gutta cavat lapidem, which means dripping water hollows out stone, meaning that perseverance allows you to achieve seemingly impossible results, just like the water flowing was able to excavate the hard rocks from the Grand Canyon. What I mean is that we didn't go from hell to heaven in a single effort. We've constantly kept improving the process over the years, attacking things that weren't ideal bit by bit, small spike of work by small spike of work. So you don't need a huge project to get to your end game. You just want to keep going along over time, but also collaboration. At least 5 teams between software engineering and SRE were involved in this process at different moments with different levels of commitment. The only way you get to persevere over so many years and to actually get collaboration from multiple teams, in my experience, is if you're able to promote a clear vision of where you want to go and the steps you want to take and which advantages are in for everybody along the way. A second lesson, which I think is nothing new either, but still seems not to be fully enshrined in SRE folklore, is that in a distributed system, configuration and state should be treated separately. Here I use the term configuration to refer to the configuration that modifies the behavior of a single system, while with state I refer to any data that describes what the intended behavior of your distributed infrastructure is. And this is data that changes dynamically over time and needs to coordination across layers. Now, what we found out over time is that while GitOps is a great tool for managing the former, it's really miserable to need a code commit to change your global routing table. It becomes a real hindrance to automation at the speed at which you can apply changes. Our experience suggests that you need a central storage of state that you can talk to via an API. And the ability for your system to react quickly to such changes is vital. Finally, this project taught a lot to us about our toolbox. First of all, you don't want your toolbox to look scary to open, like the one in this photo, as your tools need to reduce your toil, but also to improve your well-being. Take particular care in removing any pitfalls, both the ones that are obvious and that you can predict and the ones that you want. I can stress this enough. A tool that's easy to use and gives you clear feedback is much better than a tool that can do it all. It's not much better, it's going to be more successful. More people will use it. Finally, I invite you to be creative with your tooling. And that's the final story that I want to tell you about our Datacenter switchover. There's a site that listens to our public event streams of edits and plays a sound that shows a bubble for every edit that happens on Wikipedia. Now, how is this related to the switchover? Let's see if I can play the video, actually, to show you. So this is a video of one of our switchovers in 2020, so it's not as great as now. You can read the chat, thankfully, so you can see me cursing, but you can hear now, right? Edits are still flowing, so you hear them. Now, imagine during a complex operation, your eyes are your most overloaded sense, right? You have to look at logs, the chat, your graphs. This is an acoustic aid for us to know, you can hear now, you cannot hear it anymore now, but we entered the read-only phase of our operation. Now, let me see if I can manage to speed this up a bit, because it's about 2 minutes, the time it took. Sorry, no, clearly I failed, but yeah. So, okay, let me try to move on here. So, at this point, sorry, I don't know what I just did, but yeah, anyways, oh no, now you can read. Yeah, no. Abort. Sorry. But yeah, so now there's silence, right? And I compared this to the silence that you have when a spaceship is re-entering the atmosphere from space. There's a phase in which you hear nothing. There's a radio cutover when the people in mission control don't know if a spaceship is still safe or not. And then when they hear back from the people on the ship, there's a big relief. And for us, it's the same. When we hear edits flowing again, it means that the switchover, the critical part of the switchover, sorry, let me try to find it, is actually over, and edits are flowing again. Sorry, clearly I am failing to find the point, which, okay, here we are. A few edits, and then you'll hear in a few seconds the flood of people that were waiting and retrying to edit a page on Wikipedia, and actually now we're able to do it again. Okay, this is all I had for you. We are hiring somewhat. If you have questions, I'm here for them.